Hi, and welcome to the second part of this lecture on recent advances and applications of deep reinforcement learning. In this part, we will speak about deep reinforcement learning for continuous control. In this video, you see a simulated humanoid in the Mujoko robotics environment. A reinforcement learning algorithm was trained to move the joints of this simulated robot such that it would move as fast forward as possible. What is special about this domain for reinforcement learning is that the action spaces are pretty high dimensional. So it's individual forces and torques that can be applied at the different joints of the body parts, as well as the observation space, which consists of positions, angles, and velocities of the different body parts. Now, pretty early on, it was observed that standard policy gradient could be applied in principle to this setting, but that it is rather difficult to find hyperparameter settings such that learning is neither unstable nor very slow. Off-policy reinforcement learning methods like standard DQN cannot be applied because DQN, as it was presented until now, is designed for discrete actions. Now, in this section, you will learn about proximal policy optimization, PPO methods, that improve standard policy gradient methods. And you will learn about an adaptation of DQN to continuous action spaces. So in simple policy gradient, the parameters theta of a neural network change according to the parameters theta plus some learning rate times the gradient of a cost function, where this cost function here is actually the expectation of the value function, where the expectation is taken over the initial states of an episode or a trajectory. This P of S0 here is the distribution over initial states of the trajectories or episodes. Now let me remind you what the value function really is. So the value function is simply the future discounted rewards, future discounting with discount factor gamma, averaged over states and actions given the policy of the agent and the transition probabilities. Now, what do I really mean with this notation here? What I mean is that we average over all future time points and all states and next states and actions of these future time points, the discount factor times the reward that can be collected in this time step, multiplied with the probability that this transition actually happens from time step ST with action AT, where the probability of the action in that time step is given by the policy parameterized by the parameters theta, and the probability to reach state ST in time step t is given by this probability density function here, p theta, where p theta really is just the probability that state st is reached under the policy p theta and the transition probabilities that govern the dynamics of the environment. So this somewhat complicating looking expression here is the probability of trajectories until time t, so starting with the probability of the initial state and then taking an action A0, evolving the dynamics to the next state, and then with this product here over actions probabilities of actions and probabilities of next states, we get the full probability of a trajectory until, so this is the full probability of a trajectory until time t. And now we simply average out all the states and actions that can lead to the state at time t. So what is important here is that this probability of a state that can be reached at time t depends on the policy pi theta. This is not surprising because the state that can be reached by a reinforcement learning system does not only depend on the dynamics of the environment, but of course also on the policy that is taken, on the actions that are taken in that environment. Okay, so this is really the cost function which policy gradient takes to compute the gradient and update the parameters. And you have seen already in previous lectures how this somewhat complicating looking expression can be well, simplifies when one actually computes the gradient. Now the question here really is, well, how big should this learning rate alpha be? And well, should it be the same for all for all dimensions of the parameter vector theta, or what is the optimal step size that should be taken? Now, the optimal step size that should be taken can formally be found by just looking at this expression here, that we want the future discount, also the expected value for parameters theta prime minus the expected value for parameters theta for the old parameters to be as large as possible. Now, how can we find theta prime that maximizes this difference between the current, between the next parameter vector and the current parameter vector? To move towards finding out how we can optimize this update step, let us express the difference between the next parameters, the cost, or the future discounted values of the next parameters minus the value of the current parameters in this form. So I just write out again the definition for the second term in this equation. And now I do something funny, which is I just add actually an averaging, an expectation over the full trajectory, but I take this expectation over the full trajectory when sampled with the new parameters. Now this doesn't change anything. From here to here nothing happens, because the argument of this expectation still does only depend on state S0, and state S0 does not depend on the old policy, on the old parameter vector, nor does it depend on the new parameter vector theta prime. Now I do a next funny null operation, if you want. In this step here, I just express the value of state 0 here by a difference between two infinite sums. Look, important to notice is here that we start the sum at t equals 0, while here we started at t equals 1. So nothing happens. This difference in here is still the same as v theta of state S0. Now, here I just factor out the term gamma t, and I adjust for the difference in the indexing, that it runs from 0 to infinity here and from 1 to infinity there, by changing the time t, or the index in this sum here, to t plus 1, and then I can again sum from 0 to infinity. And then I factorize out the gamma to the power t. Then I'm left with gamma times v theta of st plus 1 minus v theta of st. Still the same as in the line above. In the next step now, I plug in the definition of j theta prime. And if we look back to this line here and plug that in for theta prime, then we see that actually this first part here just corresponds to adding the term gamma to the power t times the reward that can be collected in state st when transitioning to st plus 1 under the action at. I forgot to mention here that the sign has switched because I have here the two minus signs, such that in the end everything is correct here. Now this expression in here should look familiar to you. What is it? Well, it is nothing else but the advantage function that we have already seen in all advantage-based or actor-critic type policy gradient methods. Now, what is still somewhat special here is that inside the expectation, everything just depends on parameter theta, but now outside the expectation is actually taken over trajectories that are sampled from the policy with parameters theta prime. Now we can rearrange first the sums here. I took the sum from t to infinity out of the expectation, and now I just apply an importance sampling trick basically, which is instead of sampling the actions from the policy with parameters theta prime, I sample them from the old policy, but I correct here with this ratio. So when you write out the expectation, what you will see that you multiply theta prime pi theta with pi theta prime divided by pi theta, and the two pi thetas, they just cancel out again. So nothing happened again in this step here. And yet it was important to do this step because the idea of proximal policy optimization that I would like to present next, you see here I highlighted the fact that the only thing that changed in this last line is that we move from sampling from the new policy to still sampling from the old policy, the actions. Okay, let's move to the main idea here of proximal policy optimization. I copied the last line of the previous slide. Still, this difference between the expected value under the new policy minus the expected value under the old policy is given by this expectation here. And I introduced the abbreviation of this ratio here and just call it r theta prime because we're going to use this ratio multiple times afterwards. So this is r theta prime, even though it also depends on theta here. Now, as long as p theta is close to p theta, such that this expectation here is actually close to the expectation under the old policy, we can take the samples that we obtained with the old policy and just optimize this new loss here, which is, well, basically the ratio between the probability of an action under the new policy divided by the probability of an action under the old policy times the future discounted advantages. So why do we really want this, and why should these two expectations be close to each other? Well, the whole idea is that we would like to find the maximum, so the theta prime that maximizes this difference here without having actually to run samples under the new policy. So we would like to just optimize a function like this function here in theta prime without having to sample new observations or actions. And as long as this expectation here, so as long as the new policy is somewhat close to the old policy and these expectations here are roughly the same, we can maximize this new loss to find the theta primes that maximize this difference. So this really is the idea of proximal policy optimization. The word proximal here comes in because p theta and p theta prime should be proximal to each other, should be close to each other. And of course, yeah, policy optimization because we directly optimize the policy. Now let me copy over this new loss that we now found. And there are now different ways to ensure this proximity between the old policy and the new policy. One method that was proposed in 2015 is this trust region policy optimization method, where this surrogate loss, sorry, this special new loss here is maximized subject to the constraint that the Kullback-Leibler divergence between the old policy and the new policy is smaller than some parameter delta. Now the Kullback-Leibler divergence between old and new policy is a divergence measure. So it's like measuring the how much the old policy differs from the new policy, and as long as it is smaller than some theta, one can actually find guarantees such that the error that is made in this approximation is small. Now, a newer version that was proposed a little bit later is this clipped surrogate objective. Sometimes it's called the proximal policy optimization clip loss. And here the idea is to just replace this loss with a clip loss. And this clip loss here is exactly the same as our previous loss. I omitted here the explicit mentioning of ST and AT just to shorten notation, but it's the same as the original loss, unless there would be a large difference between the new and the old policy. And to restrict the difference between the ratio between the old and the new policy to some range, one can clip here, meaning that this ratio here is always between 1 minus epsilon and 1 plus epsilon. And if one clips this ratio to this range and then multiplies with the discounted advantage again, one gets an objective that keeps the policies close to each other while still maximizing, while still pushing towards this surrogate objective here that would lead to a maximal difference between the new policy and the old policy. With these new losses, we can now jump indirectly to the advantage actor critic template and improve the step where the parameters theta are updated. Now, instead of just updating the parameters theta once with the gradient of that quantity, we optimize in this step the surrogate loss, for example, the one of TRPO with the limited Kullback-Leibler divergence, or the PPO clip objective with respect to theta prime for m epochs. So we have now in proximal policy optimization an inner loop where the parameters theta are optimized with a few steps of gradient descent before we increment t and move on to the next step. Instead of just using this mini batch once, as we did in standard policy gradient or in A2C if you want, we now use this mini batch that is obtained from the K workers multiple times to move theta prime as far as possible into the right direction as is allowed by the proximity condition that is given by these losses. Yes. Let me summarize this part and ask you a few questions. To summarize, one can improve the stability and the sample efficiency of policy gradient methods by maximizing in an inner loop a surrogate function like the one of trust region policy optimization or proximal policy optimization clip. Now to the questions. With the update of policy gradient, where theta prime is theta plus alpha times the gradient of our future discounted reward, and a fixed learning rate alpha, the difference between the future discounted reward under the new parameters minus the future discounted reward under the old parameters will always be positive. Is this correct or not? This is not correct. It may be that the learning rate is too large, and if the learning rate is too large, then it may even be that theta prime does not, the future discounted reward under theta prime is actually lower than the one under theta. This is why we this is what is solved in these proximal policy optimization methods that try to guarantee that one always has an increase in this difference. But simple policy gradient does not have such a guarantee. In proximal policy optimization methods, we want to keep the ratio R, that is the ratio between the policy of the new policy divided by the old policy, so the probability of actions under the new policy divided by the probability of actions under the old policy, close to 1, such that the state visitation probabilities, the probability with which a state ST can be reached by the old policy, and the probability with which the state ST can be reached with the new policy are roughly the same. Is this correct or wrong? This is correct if we have this approximate equality between those state visitation probabilities. Then we can use the approximation that was made in this line here, such that we can estimate efficiently the quality of the updated policy. A2C uses each mini-batch once to update the policy, whereas proximal policy methods use each mini-batch multiple times, usually. Is this correct or not? This is correct. A2C
uses each mini batch really only once, whereas in proximal policy optimization methods, we run an inner loop with a certain surrogate objective function to move the parameters as close as possible to parameters that maximize this difference.